In the first chapter of this course, we are building a tool to retrieve earthquake information from the USGS API. And during this chapter, I will cover some of the materials or some of the Rust concepts. So the concepts are traits, which are for defining standardized interfaces for data sources, structs, which are used to model our earthquake data, and crates, for example, we use requests to handle network requests. And so the main struct is earthquake event. Earthquake event struct serves as our template for storing information about a single earthquake. It consists of various fields, each with a specific data type, to capture details like the earthquake's magnitude, location, time, and more. So this is one example that you can see. And this is the way that you represent the struct. In addition to these fields, we've added some special attributes that we call them derivs. Here, debug, serialize, and deserialize. And so debug makes it easy for us to print out the contents of an earthquake event in a human-readable format, which is super helpful when we are troubleshooting or debugging. Serialize helps us to transform an earthquake event object into JSON format. And it's important for a lot of APIs when we send and receive data in JSON. So we need a way to convert our struct into this format before sending it over the network. Deserialize, what it does is the opposite of serialize. So it takes raw JSON data from an API and converts it back into a neatly structured earthquake event object that we can work with in our Rust code. And once more, this is where those attributes, the derived attributes, land, just before the struct. We also have the earthquake data source trait. And this trait creates a standard way to fetch earthquake data from any source. And we have the type error. Each data source defines its own type. And you can see then the trait definition. And then we also have the call function to get earthquake data, which is fetch earthquake data here. And so this function, we have some parameters, which are data format, time range, minimum magnitude. And also we have the returns. And the returns is, okay, the vector of earthquake event when it succeeds, which is a list of earthquakes, and then error, which is of type error, which we defined just before, when an error occurred. Now let's bring earthquake data source trait to life with the concrete implementation. The USGS data source struct as our specialist when working with the USGS API. Its job is to take the parameters you give it, format, time range, magnitude, minimal magnitude, and do the heavy lifting. Build the API URL, which means that it constructs the exact web address needed to get the right earthquake data from the USGS. Make the request means like it sends an HTTP request to that URL asking the USGS for the data. And the USGS sends back the data in JSON format. The USGS data source unpacks this JSON into a tidy list of earthquake event objects that we can use. And then if anything goes wrong, like a network issue or incorrect parameters, it'll catch the error and let us know. So the implementation details for these steps are in the impl block associated with the USGS data source struct here. I commented all these steps that I talked about here and provided the description. So when we build or construct the API, and then when we make the request, and then when we handle the response. There's something that you might be wondering, this part. Why are we using blocking here? This is very important because we're going to spend some time on this line in the next chapters. So this blocking method makes the code simpler to understand, especially for this tutorial. Because as I said, for the next chapters, we're not using this blocking. It essentially pauses the current thread of execution until the network request completes and receive the response. However, in a real-world application, you likely want to switch to an asynchronous implementation. And this is what we're going to do later. Asynchronous requests allow your program to continue doing other work while waiting for the network response, making it more efficient and responsive, especially when dealing with multiple requests or when network latency is high. But we will leave this to the next tutorials, as I said. The other thing is I want to expand the map function that we see here this is the map function that I want to expand in the next slide here. So as you know, a map function is a powerful tool in Rust or other languages too that allows us to transform one collection of values into another collection. In this case, we're transforming a collection of feature objects, which is a representation of earthquakes and the GeoJSON data or JSON data, into a collection of earthquake event structs. And how does it work? So iteration. The map function iterates over each feature in the features list. In this case, this is the feature. So we iterate over this. And transformation is for each feature, it creates a new earthquake struct. It extracts the relevant data from the feature's properties and geometry fields and assigns them to the corresponding fields in the earthquake event. So we are extracting data here. And the collection is the newly created earthquake event objects are gathered into a new vector, which we ultimately return as a successful result of our function. So the map function acts like an assembly line, taking each raw feature from the GeoJSON data and transforming it into a neatly packaged earthquake event object, ready for our use. This makes our data that much easier to work with and analyze within our Rust program. Now back to error handling. Always bear in mind, error handling in any application is really important, and we are working with an external API. So we have to handle the errors. And then we saw this part that we had this type error. And I want to show you what this type is. This type is a custom type that we decided to have. And it's an enum. And it's got these elements. Unexpected status code, which is a variant which is used when USGS API responds with a status code other than 200, which is okay. 200 is okay, other than that is not okay, indicating that something went wrong with the request. And other error, this variant captures any other errors that might occur during the process, such as network connectivity issues or problems passing the response. And it leverages this error crate to automatically convert errors from the request library into our own errors. So handling the response is actually happening here in this part of the code, that we have the match statement, that we treat it or handle it when it's okay or when something happened. And then we have the status as a string. So I tie everything together with the runFetch function, which acts as the main entry point for retrieving earthquake data using our USGS data source. So after creating the USGS data source here, the instance of the struct, we can see it here in this part of the code. Then we have to run the method, which is running the fetch earthquake data method on USGS data source. And then after doing this, then we handle the results, which is easy in this match statement. If the data fetch was successful, the OK variant will contain a vector of earthquake event and represents the earthquake that match our criteria. And if there was an error during the fetching process, the error variant will hold information about the error. Example could be an unexpected status code, a network problem, or etc. The starting point of our retrieval program is quite simple. So we do some imports, define some parameters, run, and we call the runFetch method, do some printing for each earthquake event, and then we return OK. I would like to also take a closer look at the result types I use in our code. So this one is the return type of our main function. Anyhow, colon result is a type provided by the anyhow crate. It's designed for flexible error handling. And lets us work with a wide range of error types without needing to explicitly handle each one. And the empty tuple within the angle bracket signifies that the successful outcome of the main function doesn't provide a value. The function is primarily focused on side effects like fetching and printing data. So the main function doesn't have any return. And if an error occurs within main, it's wrapped in the anyhow result and propagated upward. The anyhow crate provides convenient tools for dealing with these errors, such as printing error messages or logging them. We also have the return type of the runFetch function here. And This one is a standard result type, and it's a core part of Rust's error handling mechanism. So the VEC earthquake event part indicates that a successful result will be a vector or collection of earthquake event objects. But the errors part is that custom enum defined in a project to represent different error scenarios that could arise during the fetching process. So while returning a result from the function, we clearly communicate that the function might fail and provide a structured way to handle potential errors. Now I want to draw your attention to this operator question that we have after calling run fetch. And what is this and what does it do? So this is actually a very powerful tool for handling result values concisely. So if the result value is OK value, the question extracts the underlying value and allows the code to continue. But if the result value is error of any type of error, then the question operator performs the following. It tries to convert the error into the error type expected by the function's return type. In this case, for main, we had result of type of the crate anyhow, or we had the results, the standard library Rust result type. And then it immediately returns that converted error from the function. So I'm going to run this code, the main function with cargo run. And this is the main function that we saw before, and it gets the data from this starting date time or date to this end date. So if we do cargo run, so it builds this URL, as you can see, and then it gets all the earthquakes that happened during that time frame. And then you can see the output as earthquake event this. And we have we are printing every earthquake event from that collection.